This is the setup for energy conservation with rotation. It's basically an identical lab to energy conservation on a ramp, except when we did the ramp, the original ramp lab, we used objects that slid, so we had friction that were fighting our change of energy from potential to kinetic. So the friction was fighting against us. In this case, we're going to do objects that roll, which means the friction is actually going to help us because the friction is what makes us roll. We'll probably deal with that later in the class. But for this lab, this is kind of an introduction to the idea. We're going to have two hoops, we're going to have two solid spheres, and we're going to have two solid discs. So you're going to pick one ramp. There'll be 5 ramps set up. You pick one ramp and you'll have to share the objects between the 5 ramps, but you'll stick with the same ramp the whole time. Before we actually start looking at how we will do the lab, I want to talk a little bit about potential energy or kinetic energy in a spinning object. So if I have this wheel and I spin it, I am storing energy in this wheel, and it's kinetic energy because I'm moving, just like if I had an object going forward. And our formula for the kinetic energy when I'm going linearly, we know is 1/2 mv squared. So if I take this wheel and I spin it, there's now the potential for this wheel to do work. If I take this weight and I hook it on that spoke, it picks the weight up. So we know if it can pick the weight up, then the wheel is doing work on it's changing the potential energy of that weight that I hooked on there. So that means before I put the hook on there, there was a certain amount of energy stored in this wheel. I used some of the energy to put the hook on there. Now you notice, if I go back a little bit, you notice the wheel slows down. It doesn't spin as fast after I put the hook on there. So I've got this energy. In fact, I slowed it down a little bit so I put the hook. And then see how much slower it's going? Some of the rotational kinetic energy was used up and now it's basically stopped. It was used up in doing the work of picking up the weight. So it turns out there are formulas that describe that every kind of shape has its own ability to store rotational energy. So here are the equations that we're going to use. Every shape has its own equation. If you have a solid disk, its ability to store energy is determined by what we call I, which is the moment of inertia. That's moment of inertia. And you'll see that word in your word problems. If you have a solid disk, it's equal to 1/2 m times the mass times the radius squared. Now you're going to find this mr squared is in every one of these equations. So we're going to do today, we're going to do a solid disk, a solid sphere, and a hoop. So that's why I only gave you these 3 equations. The only thing that changes is the constant in front of it, and we'll talk about why this is 1/2 and this is 2/5 and this is 1 at a later time in the class. But for right now, all we need to know is these formulas. If I have a solid disk sitting here and I let it have a solid disk, the moment of inertia for that disk is 1/2 mr squared. If I have a solid sphere like the softball, then it's 2/5 mr squared. If I have a hoop, so the middle's empty, then it's mr squared. In this lab, we're dealing with angular motion. So there's a basic rule of thumb that says any linear value you have is always equal to the radius of the object you're dealing with times the angular value, as long as that angular value is measured in radians. Or you can write it as the angular value is equal to the linear value over radius, by which I mean the linear distance an object rolls is equal to the radius of the object times how many radians it rotated. Now usually we talk about things like revolutions. We'd have to change those revolutions to radians. There's 2 pi radians in 1 revolution, so that'll come up in some of our calculations. My linear velocity, how fast I'm moving, is equal to the radius of the object times, would be if the object was rolling, times the angular velocity, how fast it's spinning. And this is the one we're going to use in our lab today. My acceleration would be equal, my linear acceleration would be equal to my radius times my angular acceleration. So this is just a rule of thumb that we're going to get introduced with, but I'll give you the specific formulas you need. But this is the general idea of how linear motion, you can change from linear motion to angular motion using this concept. So most of these equations listed here, these are the equations we're going to use in the lab today. Most of them we're familiar with. Right here is the example that the angular velocity, how fast you're spinning, is equal to how fast you're moving linearly divided by the radius. So if I want to know how fast this disc or ball or hoop is spinning coming down the hill, all I need to know is how fast it's going linearly, just like when we had our air disc that slid down. I measure how fast it gets from here to here. That's my linear, which is why when we do the lab, we'll take the delta x and the delta t like we've always been doing. We'll find the linear velocity, we'll divide by the radius of the object, and that will give us the angular, because what we need that, just like we have a linear formula, that the kinetic energy linear is 1/2 mv squared, which we're probably used to. The kinetic energy in rotational is 1/2. The I takes the place of the mass, and we'll see that some more later in the class. Your moment of inertia is the equivalent of mass for linear. This is essentially your mass, effective mass for spinning. In other words, the bigger your I, the more the object does not want to change spinning. It wants to keep spinning or not changing. This measures your inertia. It measures how much you want to keep spinning or not start spinning in the first place. Just like the mass, the bigger the mass, the harder it is to get moving or stop it from moving. And then we have our angular velocity squared. So this is the new formula that we'll use along with this. And then our total kinetic energy is equal to our rotational kinetic and our linear kinetic. So what will happen in this situation, we'll have the disk at the top, we'll let it roll. All of this potential energy, and here's your h, is from distance from here to here, and this is, so that change, that delta h right there, all that change in potential energy should turn into the total kinetic energy. And when the lab I did, it came out really well, because the friction, you have hardly any friction loss, because the friction is what makes the ball spin. So it actually aids us in getting down the hill.